Θα καλέσω στο βήμα πλέον τον δεύτερο φίλο μου, γεια σου Αλέξανδρε, τον καθηγητή τον κύριο Γεωργακίλα από το Εθνικό Μετσόβιο Πολυτεχνείο στον τομέα φυσικής και θα μας αναπτύξει τη χρήση ραδιοβιολογικών μοριακών δεικτών στην ακτινοθεραπεία. Αγαπητέ μου Αλέξανδρε, έχεις το λόγο να σε απολαύσουμε.
Ευχαριστώ. Καλημέρα σε όλους τους συναδέρφους. Ευχαριστώ Βασίλη και τη συνάδελφο εδώ. Να μου επιτρέψετε ένα πιο προσωπικό στοιχείο πριν ξεκινήσουμε. Δεν θα πάρω πολύ χρόνο. Ότι είναι μεγάλη μου χαρά, καταρχάς, ότι βλέπω πολλά νέα παιδιά εδώ. Τονίστηκε αυτό και χτες, και επιστήμονες, νέους επιστήμονες και φοιτητές. Και βέβαια δεν μπορώ να μην πω ότι έχουμε μεγάλη παρουσία και συμμετοχή και από το Εθνικό Μετσόβιο Πολυτεχνείο. Εσύ, Βασίλη, έχεις άρρηκτους δεσμούς με το Εθνικό Μετσόβιο Πολυτεχνείο και τα παιδιά είναι εδώ. Θα αναφερθώ και λίγο παρακάτω σε αυτό. I apologize. I will do the presentation in Greek for my colleagues here that do not understand Greek, but the slides will be in English, okay? I apologize for this, but the audience is requiring more to speak in Greek. So, η ομιλία είναι η χρήση βιοδικτών, μοριακών βιοδικτών στην ακτινοθεραπεία και θα προχωρήσω με αυτή την ιδέα που σκεφτήκαμε μαζί με την ομάδα μου στο Πολυτεχνείο να την παρουσιάσουμε. Είμαι και δουλεύω και εγώ χρόνια σε αυτό και άλλοι. Έγινε μια πολύ καλή εισαγωγή από την κυρία Τερζούδη στις πιο κυταρογενετικές μεθόδους. Επομένως, τώρα θα αναφερθώ περισσότερο σε αυτό. Θα πούμε κάποια πιο γενικά πράγματα και θα προχωρήσουμε λίγο σε κάποια παρουσίαση κάποιων παραδειγμάτων που μπορούν να χρησιμοποιηθούν στην ακτινοθεραπεία και ελπίζω σιγά-σιγά αυτό να μπει και στην κλινική. Να πούμε ότι, όπως ξέρετε, γιατί πολλοί από εσάς εδώ έχετε μια πολύ στενή σχέση με τους ασθενείς, ότι και ασκείτε κλινικό έργο κάτω από πολύ δύσκολες συνθήκες στον ελλαδικό χώρο, ότι σίγουρα ένα από τα μεγαλύτερα προβλήματα είναι η τοξικότητα των θεραπείων γενικά. Δεν θα αναφερθώ βέβαια στη χημειοθεραπεία, θα αναφερθώ κυρίως στην ακτινοθεραπεία. Η τοξικότητα είναι ένα μεγάλο πρόβλημα που διεθνώς βέβαια προσπαθούν διάφορες ομάδες να το αντιμετωπίσουν και να προβλέψουν ή να βοηθήσουν τους ασθενείς να έχουν μια ποιότητα ζωής πολύ καλύτερη. Αυτό λέγεται quality of life. Έτσι, και υπάρχει μια μεγάλη προσπάθεια διεθνώς. Γι' αυτό και θέλαμε με την ομάδα μου να επικεντρωθούμε λίγο σε αυτή την ιδέα. Γι' αυτό και κάτω-κάτω λέμε radiation therapy, RT δηλαδή, adverse effects. Θα πω τώρα το εξής, δεν θα σας κουράσω με όλη αυτή τη διαφάνεια, ότι ένα από τα σημαντικότερα προβλήματα μέσα και από τη δικιά μου εμπειρία και από την Αμερική και εδώ είναι ότι η ακτινοβολία επάγει, αναφέρθηκε κιόλας βέβαια από την συνάδελφο την κυρία Τερζούδη, αρχικά κάποιες βλάβες DNA, οι οποίες δυστυχώς σε πολλές περιπτώσεις λόγω ελλειπούς επιδιόρθωσης και όλα αυτά θα οδηγήσουν σε χρωμοσωμικές αλλοιώσεις, ειδικά στην περίπτωση σωματιδικής ακτινοβολίας. Όμως είναι πολύ σημαντικό να καταλάβουμε ότι τα adverse effects στην ακτινοθεραπεία δεν σχετίζονται μόνο με αυτές τις αρχικές βλάβες ή τη δημιουργία σε χρωμοσωμικές αλλοιώσεις, αλλά και με αυτό που λέμε chronic inflammation, έτσι, εδώ, και γενικά την φλεγμονή που παρουσιάζεται πολύ συχνά στους ασθενείς. Έτσι, έχουν υπάρξει κάποιες προσπάθειες η τοξικότητα αυτή να αναλυθεί, να καταλάβουμε πώς έχουμε τα διάφορα acute or chronic effects, δηλαδή αυτά που εμφανίζονται μέσα σε λίγες μέρες ή εβδομάδες και μετέπειτα μπορεί να εμφανιστούν και μετά από μήνες ή και χρόνια σε πολλούς ασθενείς. Και παραδείγματα βέβαια είναι δερματίτιδα, στο fibrosis, στους πνεύμονες και σε άλλα σημεία, και έτσι σιγά σιγά αυτό να οδηγήσει σε μια κακή ποιότητα ζωής για τους ασθενείς. Εγώ θα αναφερθώ σήμερα κυρίως στους μοριακούς βιοδείκτες. Η κυρία Τερζούδη αναφέρθηκε πιο πριν και στους κυταρογενετικούς και η προσπάθεια που γίνεται διεθνώς είναι να μπορούμε να βρούμε κάποιους μοριακούς βιοδείκτες οι οποίοι αυτοί με λίγο με αίμα ή με κάποιο άλλο υλικό από τον ασθενή να μπορούν να χρησιμοποιηθούν για να βοηθήσουν τον κλινικό και τον ακτινοφυσικό αλλά και τον κλινικό γιατρό, δηλαδή ογκολόγο, ακτινοθεραπευτή, να δώσει την πιο σωστή δόση, μικρότερη δόση αν είναι δυνατόν και τέλος πάντων να βοηθήσουν τον ασθενή. Αυτή είναι η ιδέα εδώ που υπάρχει. Τώρα, ιδανικά μιλώντας, θα έπρεπε να είχαμε φτάσει στο σημείο να μπορούν οι ασθενείς με το που πάρουμε λίγο αίμα πριν την έναρξη της ακτινοθεραπείας να είναι εύκολο να πούμε στον γιατρό «Κοίταξε να δεις, πρέπει να τον βοηθήσουμε τον ασθενή με αυτόν τον τρόπο, πρέπει να μπορεί να σηκώσει πολύ χαμηλότερη δόση, να πάρει μικρότερη δόση, αντί για 70 συνολικά γκρέι με 50 γκρέι και όλα αυτά τα συστήματα τα οποία θα βοηθήσουν για τη θεραπεία του καλύτερα. Και στον περιορισμό βέβαια του όγκου, χωρίς να χάσουμε αυτό το σημείο βέβαια πάντα. Εντάξει. Άρα ένας μοριακός δείκτης, βιοδείκτης όπως λέμε, biomarker, αυτό θα ήταν το πιο ικανό αποτέλεσμα, το πιο θετικό αποτέλεσμα. Τώρα, θα επικεντρωθούμε λίγο στην προσπάθεια που γίνεται διεθνώς για να εισαχθούν οι μοριακοί βιοδείκτες των βλαβών DNA, όπως είναι η τεχνική του γ-E2X, έτσι, της φωσφορυλωμένης πρωτεΐνης, 53PB1, όλα αυτά ουσιαστικά δημιουργούν, μάλλον ανιχνεύουν τις διπλόκλινες βλάβες στο DNA και μετά πιο εξελιγμένες μεθόδους που χρησιμοποιούμε και εμείς συχνά είναι αυτό που λέμε ο συνεντοπισμός, co-localization μεταξύ πρωτεϊνών. Αυτό έχει τέτοιο, έτσι. Και στην οθόνη. Ποιο? Με αυτό. Εδώ. Αυτό. Εντάξει, φαίνεται καλύτερα τώρα, έτσι. Ωραία. Συνεντοπισμός, δηλαδή να εντοπίσεις αυτές τα δύο αντισώματα μαζί και αυτό δείχνει ότι πρόκειται για δύσκολες βλάβες να επιδιορθωθούν. Μάλιστα, στο εργαστήριο όλα αυτά τα χρόνια έχουμε αναπτύξει και τεχνικές όπου ανιχνεύουν και άλλες βλάβες, εκτός των διπλόκλινων βλαβών, των σύνθετων βλαβών DNA. Και αυτή είναι σιγά-σιγά τα τελευταία, μπορώ να πω και 10 χρόνια ή λιγότερο μάλλον, έχουν γίνει προσπάθειες να εισαχθούν τέτοιες μελέτες και σε κλινικό επίπεδο. Έχω αρκετή βιβλιογραφία στο τέλος, δεν θέλω τώρα να σας κουράσουμε όλο αυτό. Ακούσαμε βέβαια και για το κυταρογενετικά, για το μικροπυρήνες, αυτό χρησιμοποιείται και σε κλινικό επίπεδο. Επίσης, υπάρχουν πολύ καλά αποτελέσματα για αυτό που λέμε τους δείκτες απόπτωσης. Δηλαδή, παίρνουν αίμα από τους ασθενείς πριν ξεκινήσουν την ακτινοθεραπεία. Υπάρχουν δύο πολύ μεγάλες μελέτες στο ευρωπαϊκό επίπεδο και βλέπουν δείκτες απόπτωσης, διακυταρικού θανάτου δηλαδή, πώς ανταποκρίνονται τα κύτταρα ex vivo, όπως λέμε, στην ακτινοβόληση και από εκεί έχουν κάνει μια πολύ καλή πρόβλεψη σε αρκετές περιπτώσεις. Όχι πάντα βέβαια, εντάξει, αλλιώς θα ήταν σίγουρα οι καλύτεροι δείκτες. Και για την τοξικότητα μετά, να μειώσουν την τοξικότητα στους ασθενείς, για να βοηθήσουν τους γιατρούς δηλαδή να μειώσουν την τοξικότητα. Αναπτύσσεται τώρα τελευταία και ενδιαφέρει πάρα πολύ, πιστεύω, και κάποιους ανθρώπους, σαν την ομάδα του Βασίλη του Γοργούλη, που έχουμε και την συνεργασία και βρίσκεται εδώ και η κυρία Χαβάκη και η κυρία Τρέμι πάνω στο senescence. Αναπτύσσεται και μια τέτοια κατεύθυνση προς τέτοιους μοριακούς δείκτες. Είχα πει και πιο πριν ότι σημαντική είναι και αυτή το inflammation, η φλεγμονή, γι' αυτό και πολλοί αρχίζουν και ψάχνουν, και έχω τις αναφορές, για δείκτες οι οποίες σχετίζονται κυρίως με τη φλεγμονή, όπως είναι ο TGF, η Ιντερλευκίνη 6 και κάποιους άλλους. Και βέβαια η high sensitivity CRP, που ξέρω ότι σε κλινικό επίπεδο χρησιμοποιείται πάρα πολύ. Κάποια παραδείγματα, να μην σας κουράσω. Πράγματι υπάρχουν μελέτες που δείχνουν ότι κάποιους από αυτούς τους μοριακούς δείκτες έχουν καταφέρει να βοηθήσουν στο να προστατέψουν τους ασθενείς από εκτεταμένες βλάβες, παραδείγματος χάρη στο σηκώτη, στο liver, μετά από την ακτινοβόληση. Μια πολύ μεγάλη μελέτη σε ευρωπαϊκό επίπεδο έδειξε ότι και πρωτεΐνες που σχετίζονται με την επιδιόρθωση, όπως σας είπα, δηλαδή η γ-η2αχ, γ-η2X, η ATM, που είναι βασική πρωτεΐνη επιδιορθωτική, σχετίζεται με την τοξικότητα, δηλαδή όταν βλέπανε αυξημένα επίπεδα στο αίμα αυτών των πρωτεϊνών, βλέπανε πολύ χαμηλή τοξικότητα. Σε άλλες περιπτώσεις που ήταν πιο χαμηλά τα επίπεδα, βλέπανε αυξημένη τοξικότητα στους ασθενείς. Τώρα, επειδή αναφέρθηκε και η πρωτονοθεραπεία και η θεραπεία που αναπτύσσεται κυρίως είναι τα πρωτόνια, ευχόμαστε και στην Ελλάδα να υπάρξει αυτή η δυνατότητα. Είναι πολύ ευχάριστο ότι έχουμε μαζί μας τον καθηγητή Κουμένη, ο οποίος έδωσε μια ομιλία χθες και τόνισε ακριβώς την ανάγκη και την υπεροχή της πρωτονοθεραπείας σε πολλές τέτοιες περιπτώσεις. Και βέβαια ακούσαμε και για το ακάρμπον, για τον άνθρακα. Και εκεί λοιπόν, υπάρχει μια μεγάλη προσπάθεια που γίνεται διεθνώς να καταλάβουμε τώρα πια, όχι τόσο για την τοξικότητα, αλλά να καταλάβουμε την ακτινοθεραπεία, πώς επιδρά κυρίως στην περιοχή, θα πω για τους φυσικούς, του Bragg Peak, δηλαδή το SOBP region, όπου εκεί spread out Bragg Peak δηλαδή, όπου εκεί μπαίνουν markers βλαβών, αρχικά με κύτταρα και μετά εξελίσσονται αυτό καλύτερα με ζώα κτλ. Και βλέπουν τι είδους βλάβες, τι βιολογικές προεκτάσεις έχει η περιοχή αυτή και σε καρκινικά κύτταρα, αλλά και σε υγιή, γιατί και αυτό βέβαια μας ενδιαφέρει. Γιατί λίγο να ξεφύγουν τα σωμάτια έχουν τρομερές επιπτώσεις και στα υγιή κύτταρα. Και παραδείγματα έτσι που έχει και διεθνώς, και εμείς έχουμε τέτοιες εικόνες, όπου μπορεί κανείς να συσχετίσει τις βλάβες και να καταλάβει καλύτερα σε αυτές τις περιοχές, όπως λέμε, του υψηλού ελιτή. Τι γίνεται, γιατί στο Bragg Peak ουσιαστικά ανεβαίνει τρομερά η αποτελεσματικότητα των σωματείων. Να προχωρήσω. Λοιπόν, παραδείγματα είναι, δεν θέλω να τα διαβάζω όλα και να σας κουράσω. Βλέπετε εδώ και μια πολύ μεγάλη μελέτη που έχει γίνει, Molecular Profiling for Predictors of Radiosensitivity in Patients with Breast or Head and Neck Cancer. Και βλέπετε κάποιους από αυτούς τους βιοδείκτες. Μια κατηγορία ειδική είναι τα gene variants, δηλαδή οι πολυμορφισμοί, όπου εκεί γίνεται πάρα πολλά χρόνια μια μελέτη. Έχουν βρεθεί ακόμη και εμπορικά, υπάρχουν πακέτα που δίνονται για να ελέγχουν τα γονίδια και να γίνεται μια πρόβλεψη της ακτινοβαισθησίας του ασθενούς σε κλινικό τώρα επίπεδο. Υπάρχουν και κάποιες εταιρείες που δειλά-δειλά το πουλάνε αυτά, τα πουλάνε και συνεργάζονται με νοσοκομεία και στην Αμερική αλλά και στην Ευρώπη. Μάλιστα στην Αμερική αυτό έχει προχωρήσει πιο πολύ. Εντάξει. Παράδειγμα είναι αυτό εδώ που είναι και εμπορικά διαθέσιμο. Αυτό το Rila, Nova Gray Rila Prostate, που είναι για τους ασθενείς που υπόκειται σε ακτινοθεραπεία για τον προστάτη. Έτσι, αυτό είναι εμπορικό. Δηλαδή υπάρχουν εταιρείες που δειλά-δειλά μπαίνουν σε αυτό το χώρο και πουλάνε αυτά τα τεστ. Και συνεργάζονται βέβαια με νοσοκομεία και με τους κλινικούς γιατρούς. Βέβαια δεν υπάρχει πολύ εκτεταμένη αυτή η χρήση αυτών των βιοδεικτών. Ακόμη τουλάχιστον, αλλά μελλοντικά πιστεύουμε ότι θα γίνει. Εμείς ήμασταν από τα πρώτα ίσως γκρουπ που συνδέσαμε ουσιαστικά τις βλάβες DNA, βιοπροφορικά τουλάχιστον, αλλά και πειραματικά. Δεν θα μπω τώρα σε όλες αυτές τις λεπτομέρειες, γιατί το έχουμε κάνει και in vivo, σε ποντίκια, με συνεργασίες βέβαια με το εξωτερικό, αρχικά με το NIH, και είδαμε ότι υπάρχει μια τρομερή διασύνδεση πολλών από αυτών των γονιδίων που σχετίζονται με κλινική ακτινοευαισθησία, πάντοτε γι' αυτό μιλάω έτσι, όχι κυταρική, γιατί είναι εντελώς διαφορετικό, και βρήκαμε molecular signatures, τα έχουμε δημοσιεύσει παλαιότερα αυτά, και βλέπετε ότι υπάρχει μια τρομερή διασύνδεση Μια τρομερή διασύνδεση μεταξύ των DDR genes, δηλαδή γονίδια και πρωτεΐνες βέβαια, που αναλαμβάνουν την επιδιόρθωση του DNA, με δύο πράγματα. Και με την φλεγμονώδη αντίδραση, το immune response, το inflammation response, με συγχωρείτε, και immune response του νοσοποιητικού συστήματος. Δηλαδή, τι γίνεται. Και σιγά σιγά αυτό έχει ανέβει πάρα πολύ τα τελευταία χρόνια. Υπάρχουν τρομερές δημοσιεύσεις σε Nature, Science κτλ. Ότι υπάρχει μια επικοινωνία του συστήματος απόκρισης στις βλάβες, DNA damage response, του DDR δηλαδή, με το νοσοποιητικό σύστημα και με τη φλεγμονώδη αντίδραση που υπάρχει. Άρα, στον ασθενή, στους ασθενείς που υπόκειται σε ακτινοθεραπεία, λόγω της ακτινοβολίας, ξεκινάει μια τέτοια διαδικασία. Και γι' αυτό συχνά, και ίσως μπορεί και κλινικοί εδώ, αν είναι γιατροί, όπως ο Βασίλης, μας το πει αυτό, αν βλέπετε στους ασθενείς μεγάλη φλεγμονή μετά από καιρό.
Ετοιμάζουμε για το σχόλιο μετά.
Εντάξει. Βέβαια, εντάξει, δεν θέλουμε να πούμε ότι ακόμη όλα είναι τέλεια. Είναι σε ανάπτυξη το φαινόμενο, τη έρευνα. Πιστεύουμε ότι θα υπάρξει όμως προσπάθεια αυτή για να μπει στην κλινική, η χρήση των βιοδεικτών. Νομίζω θα ωφελήσει τους ασθενείς, γενικά. Όλα αυτά γίνονται για να βοηθήσουν τον γιατρό και τον ακτινοθεραπευτή να βοηθήσει τον ασθενή. Όλα αυτά. Δεν γίνονται για άλλο λόγο και όλες αυτές οι προσπάθειες. Και βέβαια τον ακτινοφυσικό, που εδώ είμαστε σε ένα συνέδριο ιατρικής φυσικής, τον ακτινοφυσικό, τον φυσικό ιατρικής, να δώσει τις πιο σωστές δόσεις ή να βοηθήσει τον γιατρό να δώσει τις πιο σωστές δόσεις, να μειώσει τη δόση και έτσι σιγά σιγά ο ασθενής να έχει μια καλύτερη ζωή. Υπάρχουν πάρα πολλές τεχνικές, μοριακές, deep sequencing, δηλαδή ανάλυση δεδομένων, γενετικών δεδομένων, με αλληλούχηση. Τέλος πάντων, υπάρχει μια τρομερή προσπάθεια που γίνεται διεθνώς, κυρίως στην Ευρώπη και στην Αμερική. Μάλιστα στην Αμερική θέλω να πω ότι αυτά έχουν πιο πολύ καιρό προηγηθεί. Και αυτή η δουλειά που σας λέω και έχει προκύψει και από δικά μας πειραματικά αποτελέσματα και βιοπροφορικής και γενικά από τη βιβλιογραφία, είναι ότι υπάρχει μια τρομερή διασύνδεση μεταξύ του DDR, το βάλω εδώ, μεταξύ του DDR, του inflammation response, δηλαδή της φλεγμονής, και του immune response. Τώρα, υπάρχει ένα κενό γνώσης για όσους ασχολούνται με το θέμα στις λεγόμενες χαμηλές δόσεις. Θα πείτε, μα καλά, στην ακτινοθεραπεία δεν με ενδιαφέρουν οι χαμηλές δόσεις. Έχω 2 γκρέι και πάνω, ή 2 γκρέι τέλος πάντων. Να πούμε εδώ ότι αυτό δεν ισχύει μόνο, ισχύει μάλλον μόνο για τον όγκο, ενώ για τις περιοχές που είναι γειτονικά στον όγκο, οι δόσεις είναι πολύ μικρότερες. Άρα, εδώ οι χαμηλές δόσεις σχετικά στους υγιείς ιστούς, το normal tissue toxicity που εμφανίζεται συχνά, μπορεί να σχετίζεται με κάποια τέτοια φαινόμενα που πρέπει να αναλυθούν. Και έχουμε ουσιαστικά ήδη δημοσιεύσει και έχουμε εδώ τη συνάδελφο από το Πανεπιστήμιο της Θεσσαλίας, την κυρία Θεοδόρου, που έχει πιστέψει σε αυτούς τους βιοδείκτες. Να είσαι καλά. Και πιστεύουμε ότι μπορεί αυτό σιγά σιγά να μπει, να συνεργαστούμε οι ραδιοβιολόγοι, οι ραδιοβιοφυσικοί τέλος πάντων, με εσάς τους κλινικούς, για να μπορέσουμε να κάνουμε τη ζωή των ασθενών καλύτερη. Δηλαδή θέλω να εμφυσίσω και όπως είχα πει και πριν 2 χρόνια την προσπάθεια αυτή της ραδιοβιολογίας. Νομίζω η ακτινοφυσική εσείς έχετε αρχίσει τώρα σιγά σιγά να το αγαπάτε περισσότερο το αντικείμενο. Τελειώνω. Να πω ένα μεγάλο ευχαριστώ σε όλη την ομάδα του εργαστηρίου και τους μεταδιδάκτορες που κατά καιρούς έχουν συνεισφέρει σε αυτές τις δουλειές. Με βοήθησαν πάρα πολύ σε αυτή τη συγκεκριμένη ομιλία οι υποψήφοι διδάκτορες του εργαστηρίου. Η κυρία Κικούδη είναι εδώ σήμερα και ο κύριος Βασιλόπουλος. Η κυρία Κικούδη είναι ακτινοφυσικός και ο κύριος Βασιλόπουλος είναι βιολόγος. Και βέβαια όλα τα παιδιά που είναι σε προπτυχιακό επίπεδο, που κάνουν έρευνα και συνεργάζονται και με ιδρύματα άλλα και με πανεπιστήμια άλλα. Και ένα από τα κέντρα είναι σίγουρα ο Δημόκριτος. Η κυρία Τεζούδη είναι εδώ, την ευχαριστώ πάρα πολύ για τη συνεργασία. Ο κύριος Κουμένης, έχουμε συνεργασία με τον κύριο Κουμένη. Και βέβαια από το εσωτερικό την ομάδα του Βασίλη του Γοργούλη και άλλους ανθρώπους που έχουν πιστέψει σε αυτές τις ιδέες. Ευχαριστώ πολύ.
Ευχαριστούμε πάρα πολύ τον κύριο Γεωργακίλα.
Να είστε καλά.
Είναι πραγματικά πολύ ενδιαφέροντα.
Την έχω στο τέλος.
Let's welcome Professor Seco, heading the Division of Biomedical Physics and Radiation Oncology from the German Cancer Research Center. He'll talk about the impact of oxygen in radiation therapy and radiobiology.
Okay, good morning, everyone. I know I'm the last talk before lunch, so hopefully I can keep you entertained for a few minutes. I had problems yesterday with the laser pointer. Today is working better. All right. I'm going to talk about oxygen. So oxygen is the single most important parameter, in fact, when you do radiation, and I want you to explain to you. So most of you think you understand oxygen, but it's not really straightforward, right? So we need, in fact, not only oxygen, but we need carbon dioxide. You need both of them to establish a very high level of metabolism, for example, in the cells. But the oxygen comes in through the lungs, they enter into the bloodstream, through the hemoglobin, and the majority of the oxygen that we get, this is active transmission, so active transport through the hemoglobin, but when it leaves the hemoglobin, it's a passive diffusion process. So it exits the hemoglobin and it diffuses through the intramembrane spaces, and that's passive. There's nothing there pushing it or pulling it, okay? So it's really not an active system, it's a passive system, right? So we need the blood vessels for that, and we need the hemoglobin that transport most of the oxygen. Now, the variety of oxygen in our body varies significantly from person to person, but these are rough numbers. We are usually at 100 milligrams of oxygen at the arterial level, which is roughly 14%, right? And you can breathe slightly lower levels if you want to, but usually the optimal is around 12 to 14%, depending on certain volume of lung breathing. And the venous lung is usually at 14 millimeters of mercury. And you see the difference in oxygen from tissue to tissue is significant. So skin, for example, has a relatively low level, but you have liver and brain. Brain is usually higher, and then you have the direct contact with the air, like, for example, the trachea. So there are different levels of oxygen. And we usually tend to quantify this as CO2 max, the amount of oxygen that we have in capacity to bind to the hemoglobin. And this is very different from male to female also. This plays a very big role. Okay. So normally we are at 200 milligrams of O2 per liter, or something like 1.3 milliliters per O2 of gram of hemoglobin. So that's a lot. We have enough oxygen. We have to thank the hemoglobin for that, right? But we have to always keep in mind that the oxygen flows through the arterial to the venous. So you always have a certain level of oxygen in your body. It doesn't matter what you do. If it's working perfectly, you have around 14 milliliters, that's the venous one, but you have that amount, all right? And the amount of oxygen that is available to any tissue is usually just this difference. So this is the difference of how much oxygen is present to most tissues, and you see it's around 6 to 8 milliliters per deciliter of blood, okay? Now, if you remember basic physics, the pressure of air on a liquid forces some gas to be diluted in the liquid, okay? This is usually called the Henry constant, for those who know Henry. Some of you might know him. But it has a very small impact, okay? It sits down here at 2%. So dissolved oxygen through just pressure, right, is very small. It's 1 to 2%. The rest, 98%, comes through the hemoglobin transport. So you really need hemoglobin to transport oxygen. If you want to increase oxygen uptake in your cells, I would ask you to see who's awake. How would I do that? How would I increase my oxygen uptake in cells? Anyone? Well, hyperbaric, I was thinking, but hyperbaric doesn't increase a lot. It increases 1 or 2% per atmosphere, so it's really not the best way to do it. Any other ideas? Huh? So like EPO and stuff like that, you can give the person EPO or stuff like that, you increase hemoglobin, right? But let's do a healthy approach. How would I increase oxygen in the cells? Running. Exercise. So the simplest way to increase oxygen is hyperventilation. You hyperventilate by running, doing exercise. Just hyperventilation, you can almost increase 30-40% the oxygen that is available because you're running through hemoglobin faster. Okay? So one way to increase oxygen is the simplest, hyperventilation. You can give drugs to increase hemoglobin itself, but oxygen pressure is not the way to go usually. So if I was to really increase oxygen pressure, I have to go to 10 atmospheres to get 10% or 15% increase, okay? So pay attention that the key reason you have oxygen in everywhere in your body is controlled by hemoglobin, okay? But the cell functions with two gases, oxygen and carbon dioxide. You need both of them, okay? Don't ever forget, you try not to forget the need of carbon dioxide. That's critical for maintaining cell in a very constant pH and allowing it to function, okay? But oxygen is driven by this hemoglobin, okay? Okay, what about the radiation response? That's why I'm here after this initial introduction. So, radiation breaks up water. Let's start with the simplest case of our tissue is all water, all right? Radiation breaks up water and produces a variety of these radicals. You will see a radical when there is a dot. That's usually an indication that there is an unpaired electron and it's reactive. It can either receive another electron, it's an oxidizing element, or it can donate an electron, it's a reducing element, okay? Oxidation is capture, reduction is donor, okay? OH is an oxidizing element, that's why it's red, and the black one here, H and E solvent, they are reducing elements. They are electron donors, all right? So radiation breaks up OH. You saw two really nice talks this morning. Radiation breaks up OH, and it is only when it hits the OH that it becomes toxic. And the reason is the OH is unstable. And what does it need? It needs an H. So this is called hydrogen abstraction. It's going to go steal hydrogen from somewhere, right? If you remember the DNA, there are three molecules in the DNA. There's the phosphate, no H. There's the sugar, lots of H. And there's the base, which has some H, right? So the DNA damage, the OH-based DNA damage, comes from stealing H's primarily from the sugar molecule. Okay, it can also remove some from the DNA base, okay? So this hydrogen abstraction creates an instability, a structural instability, right? That now can be repaired, okay? So it's in a position that it can be repaired. But if I have oxygen, if I can get oxygen to rush to the point before anything else, I can fix this damage. Okay, so this is the idea from 1955, 1956 when it was initially published by Alexander, and it's been kind of around since 2021 or 22 when we started to challenge it. But it's really important that you understand what's happening. If the O2 attaches to a sugar molecule, I have a change of molecule. I convert it into an alcohol. So I have a sugar that's binding the structure of the DNA. If it now becomes an alcohol, it's going to open. Okay? If it opens, it's structurally unstable and it will break. There's your damage, your DNA damage, okay? So OOH, which is missing over there, the H will come in. OOH is now an alcohol. I don't have a sugar anymore structuring the DNA, holding as at the base. I have now an alcohol that potentially can change it. So this is a problem. This is where it happens. Here, I have a structural damage, okay? Okay, it's chemically induced. Please forget about the alpha LET that was mentioned this morning. This is for now just chemically induced. I will come back to the alphas and that later, all right? Okay, so the first time to ever study this was Gray, Wright, and Flanders. They published these first ideas, and they quantified OER, which is oxygen enhancement ratio. And this is usually quantified on a clonogenic survival, where you have dose on the horizontal axis and survival. And these two curves, the white dots represents no oxygen, so hypoxic cells, and the black line represents oxygenated, and you pick an endpoint, so 10% survival, and you calculate the ratio of these 2 points. This is what the OER is, the ratio of the dose for this one, which is roughly 16, to the dose for this one, which is roughly 7, right? That's the OER, how we define it. We tend to define it at 10%, but if you can measure it at 1%, which is usually not easy to do, you can also define it at 1%, but it's mostly done at 10%, right? Because 10% we can measure both well, okay? So the endpoint is up to you to define. Most of the groups quantify that at 10%. We tend to go for 1% because it's linear in that regime. So there we tend to prefer the linear response. Okay, when you measure this as a function of oxygen, this oxygen enhancement ratio, you have a huge variation So on the horizontal axis again, you have oxygen, and this time it's millimeters of mercury. So 10 millimeters of mercury is roughly 1%, 20 is 2%. This is at body temperature, 37 degrees, okay? And hypoxic cells usually give 1, okay? As you change a small amount of oxygen, you have a very rapid increase in sensitization of the cells. They don't have to be cancer cells. They can be any type of cells, okay? So this rapid increase eventually saturates very quickly around 30 to 40 millimeters of mercury. So you see the saturation here, then it goes up a little bit, but it's very little. The bad thing is the cancer cells have low oxygen. So for the same level of oxygen, I'm losing the fight. I'm introducing more toxicity to the healthy cells, all right? So if I irradiate cancer cells and tissue at the same time, I lose. Right? I'm intrinsically sensitizing more the healthy tissue than the cancer cell, which is a disadvantage with the oxygen, right? So I have to be smart and do other things. But the key point is this factor varies from 1 to 3, very rapid increase in the beginning to a few millimeters of mercury, then it saturates very rapidly, and this is how we quantify oxygen in radiation. This is an in vitro situation, okay? All right, now I want to also give you an idea of time. How early does the oxygen have to be there? Can it be there 5 minutes later after the radiation? Or does it have to be right there at the radiation time? Or can it be just before? So these temporal studies were done in the 70s. And they found that it has to be present within a millisecond. So just before, it has to be there. If it's not there within a millisecond, it doesn't work anymore, okay? So these studies were done based on certain things, and I wanted to, here is the key. So in the 1970s, they had a way of pre-mixing oxygen just before irradiation. It was a really nice system, and here you have different survival curves where nitrogen is hypoxic, and you see different times, 40 milliseconds at 10%, 1%, and you see the timing getting closer and closer and closer, right? So what happens is, if you give oxygen after, there is no sensitization. You have to give it before, a few milliseconds before, right? You start to see this, right? And there was another follow-up study that was really careful, and they managed to show this for different times, what was the half-life of oxygen, okay? So here, you have oxygen before radiation, 1 millisecond before, 2 milliseconds before, 3, 4, 5. You have enormous cell kill. But as you start to give it after radiation, you have a sudden increase in survival. So now it's 1 millisecond after 2 milliseconds, 3 milliseconds, you have this very sharp increase in survival. So they estimated that you have to have it there within half a millisecond. That's the half-life, right? Notice how fast it increases, right? So gas, the oxygen gas, has to be present at the cell level right at the time of radiation, preferably a few milliseconds before. So this is an important time because it tells you how fast effectively the oxygen takes to diffuse, right? Roughly, it takes 1 millisecond to diffuse a very small distance of a few millimeters, and that's kind of what fits in here, all right? So this study was done in 1973 by Michael et al., and it very clearly shows the importance of time, right? 1, 2, 3 milliseconds, and this is critical for us for oxygen sensitization. Oh, I just wanted to mention my apologies for that. Okay, one more thing. You can control oxygen through something called a thiol. Thiols are SH molecules, the molecules that have some radical with an SH, a sulfur hydrate. And these are really important because most of the protection against oxidizing elements are based on these thiols, SH elements like glutathione. Who's heard of glutathione? Anyone? Please, 2 or 3 people. Okay, the rest are sleeping, I can see that. Glutathione is one of the most important molecules in your body. With superoxide dismutase, they protect you from oxidizing elements, right? So thiol, GSH, is that glutathione. And they also studied the impact of glutathione, GSH, in radiation response. And they found that GSH is potentially the driver of the oxygen damage. So glutathione is the final step before hydrogen peroxide becomes really toxic. If you don't have GSH, which is this negative one here, right? If you don't have GSH, you are extremely sensitive to radiation damage, extremely sensitive. So this is a very important system that you need, right? Or you will not survive going to the beach, for example. So that glutathione, upregulated, downregulated, and complete knockout, right? So you see that you're extremely sensitive to one molecule. or similar things that like peroxyredoxin. These molecules play a very big role. Okay, well, the millisecond is the key. The endpoints, you have to really be careful how you study them. Oxygen connexus plays a very important role in this, and glutathione is the driver. Okay, now let's connect time and space. So time is temporal time before oxygen is present. Space is my diffusion. Okay, many of you know that the distance that the oxygen can diffuse depends on the diffusion constant of the medium, the time, of course. And this is your kind of like effective distance that you will travel, the root mean squared displacement of your diffusion. So you have something that's diffusing. You have the Einstein-Smolensky equation that tells you very easily that it's connected to two parameters. Time I already told you about, and diffusion is the property of the medium. And this diffusion depends on two very important parameters, in addition to temperature, of course. Is this the A, which is the radius of the molecule, and this eta, which is viscosity, right? Viscosity is how sticky your medium is. That's kind of like a simple way of explaining it, right? You run your hand through water, it flows. You run your hand through oil, it's very sticky. And blood is also very sticky. So if you run your hand through a small amount of blood, you see that. So viscosity, the higher the viscosity, the worse it is, the less it diffuses. So that's why we're very lucky to have so much water in our body. It's because of that. The viscosity plays a major role in diffusion. Okay? And the size of the molecules, gases, O2s, are very small, so they have very small radius, which is perfect. Temperature. How can temperature be important for radiation? Anyone have an idea? Imagine that you're doing space travel. I want to go to Mars, 2 years. How am I going to reduce the amount of radiation effect? Radiation effect. I'm always going to get radiation, but the effect. I can freeze my astronauts, you see? If I freeze my astronauts, I reduce radiation effect. This was one of the ideas that was proposed, but freezing someone at the moment is not a really good stable thing. But someone investigated what happens if I drop the temperature from 37 degrees down to 33 degrees, and I get a 20% in sparing, right? So temperature can be a very important thing, right? You see all those Star Wars travels where they go into subspace with all these fast things and then they don't sleep. You know there's something wrong, right? They have to sleep, and preferably at low temperature. Keep your body low, you reduce the effect of radiation damage. I will skip that. Okay, the other thing is the spatial size of your diffusion. So you've seen very big tumors, and some of you might have seen it in fact. Very big tumors have a certain diffusion distance of oxygen. So yeah, this diffusion distance is usually around 170, 180 micrometers. So it's very, very small. And as the tumor is consuming oxygen, within these 200 micrometers, there's no oxygen anymore. So you see here is a spatial problem of radiation. I can kill the tumor, all of it uniformly here, in the first one. Here now I have a core that is really difficult to treat. So hope that is clear to you. This is the donut problem of radiation, okay? It is a major problem, okay? And what we try to do is we try to identify how big this core is. And so in vitro studies, it's relatively easy. You look for a second kick, okay? But you have to go to very, very high doses. It's not so common. But in vivo, when we treat patients, we don't have that luxury. So we fractionate. So we know that every day I give a certain amount of radiation and it kills the outer ring of the donut. I have a new one, and this takes a certain time of reoxygenation, and so on and so on. So the reoxygenation is an important thing, right? So the more I reoxygenate, the better it is at very much control, okay? How long does it take for reoxygenation? It takes roughly, this is the wrong slide. I don't have it here, my apologies. So it takes roughly 6 hours for this reoxygenation from here to here. So that's why you wait 24 hours. You can wait 6-7 hours for this reoxygenation to occur, and then you can treat again, all right? Now, hypoxia is an important factor, and when you have a hypoxic tumor, you have something called HIF, hypoxia inducible factor, which was identified by these three gentlemen in the late 90s who won the Nobel Prize for it. So when a tumor becomes hypoxic, this hypoxic inducible factor, HIF, changes the tumor properties and it becomes significantly more aggressive, okay? HIF is an important regulator of everything. It's a transcription factor that when it's in presence of oxygen usually gets destroyed, But if it's not, it basically changes the tumor, making it extremely more aggressive. It increases proliferation, metastasis, increases everything. So when we treat in patients, we try to see which tumor are like this and which are not. That's why when we work with clinicians, usually they tend to go straight to PETs for slightly bigger tumors to check, is there a hypoxic core? If there is, you've upregulated very likely HIF, and now that's triggered a really significant change. And I wanted to provide you the path. HIF is usually, it's destroyed with oxygen, and it gets broken down into small pieces in degradation. So we have constantly HIF present. When we don't have oxygen present, HIF makes it into the nucleus and transcribes. Since it's a transcription factor, it completely changes the behavior of the tumor, making it more aggressive. Okay? So we need oxygen to break down HIF. Without oxygen, HIF really becomes aggressive. Okay. I also want you to understand the difference of extracellular distribution, intracellular distribution. So it's very common to see pictures like this, where I just explained. The distance to the blood vessel is the key for hypoxic conditions, right? These are usually related to late stage. The tumors become so big, right, that the inner core is hypoxic. But you could also have intracellular hypoxia. We showed this 2 or 3 years ago in a study that we did, that there are so many membranes here that the diffusion of oxygen can be slowed down such that in the core you have low levels of oxygen, right? So this is inside a cell, okay? It doesn't happen through the whole cycle, it happens in parts of the cycle. And because you see so many different membranes as I cross through the cell, I can literally slow down oxygen diffusion, right? It's a physical barrier. So what we showed, so this is the reoxygenation, here is the timing. I want to go to the other one. The intracellular part, we usually assume that oxygen diffuses very fast through the cell, right? And in many of these assumptions, we assume that all the oxygen level in all the organs inside, organelles, that they're all the same. And this only happens if the diffusion is fast enough and the membranes are not blocking the oxygen transport. Under these conditions, you have a fast diffusion, the consumption is too slow, and oxygen is the same inside and outside. You have a very simple extracellular matrix equals the nucleus. But you can have a situation where the diffusion is much slower now than the consumption. So if I'm removing oxygen or slowing it down, I can change the whole dynamics of oxygen in the cell. And how do I do that? Well, you have to have a special type of problem. So most membranes that we have are phospholipid, they're all phospholipid based, but some of us have more cholesterol in the membrane and others don't. Cholesterol literally makes the membrane rigid. So if you have a flexible membrane, oxygen can flow through it. If you have a rigid membrane, oxygen cannot flow through it, right? So here you see the difference of no cholesterol, a lot of cholesterol, and this is what most of us have. We have a small amount of cholesterol that makes this membrane a bit rigid, but most of the time there is a path through which oxygen can flow. And we studied this. We showed that if we change the cholesterol content, you change the diffusion speed. And with that, we showed that this can effectively modulate the amount of oxygen that's reaching the nucleus. Okay? So this is a diffusion problem. Each cell, each person that has more or less cholesterol in their membrane can have a change in certain types of cells. People have shown in the recent years that cholesterol builds up in different membranes, and this plays a big role, in my opinion, also in radiation response. Okay. Now, I have an opportunity here for all of you who are biologists hardcore, and I'm looking at other people because I've just told you about the oxygen fixation hypothesis, but I'm going to criticize it now. So I'm giving the opportunity to a hardcore biologist to evacuate the room so that I don't get killed in the next 5 seconds. Okay, so if you want to stay for the next 2 minutes, I'm going to criticize what I've just told you, okay? But this is important because you have to understand what's the problem at the moment. So the key concept of oxygen damage is this fixation. It's been around since 1954-55 when it was initially published, okay? We've been using it since then, but Flash came along and, of course, challenged this. Now, if some of you attended my talk yesterday, I might have mentioned a little bit about Flash, okay? Flash suddenly raised some questions about this idea. And I mentioned that already yesterday. It's high dose rates, high doses. But Flash specifically targets oxygen. So we can study this mechanism with FLASH. And that's what we've done in the lab, okay? And the first discovery of FLASH was in 2014 by the Vincent Fauvedon group. They published that. It was a really breakthrough, but the last 3-4 years, a lot of it has been going into the mechanism, okay? Okay. At the heart of FLASH, before our study in 2021, was something called oxygen depletion. Right? FLASH removes oxygen so fast that it cannot do damage. This comes from, in fact, the fixation idea. If I fix damage with oxygen, then if FLASH depletes oxygen, then I have no damage. Okay? So this is where the oxygen depletion comes from this reaction here. Okay? FLASH produces a lot of radicals at a very short amount of time. These radicals wipe out O2, so there's no damage. There's no fixation. That's the concept that was around for many years. All right? So, in principle, I should be expecting damage proportional to oxygen, no damage. Simple, okay? We published a study in 21 showing, no, that's not the case. Which is the case that shows that there is no oxygen depletion. Right? In fact, you have more oxygen with FLASH. And so effectively, we come back to this equation, what we showed that this doesn't happen. O2 depletion does not happen. In fact, what you do have is more oxygen, not less oxygen with FLASH, but you have more oxygen but less damage. Literally the opposite of what I just told you. Okay? This is where I finished more or less yesterday. But if I have more oxygen and less DNA damage, doesn't that also raise questions about that? So I literally have the opposite now. So the fixation in principle is also not true. Okay, so what we've proven in my lab is the red one. The blue one is a bit more complicated to prove because we would have to have the mechanism. So we do, in fact. And in my lab, we've literally blocked oxygen damage chemically. So oxygen is present, we just block the effect. And we see a significant increase in survival. But oxygen is present now. We do it with oxygen present at any level. So we have increased survival factor 4, 5, 6 survival by just blocking the effect. Okay? And that's my last slide. I want to thank everyone and the patients just before lunch.
Thank you so much for your comprehensive presentation. Are there any questions from the audience? Because I have some.
Go for it.
Some for you, dedicated to your presentation. The first one is more like a comment. We saw from your presentation the Einstein formula about the role of the temperature in terms of the damage producing by oxygen and radicals, whatever. Because now I'm going to wear the hat of clinician, not physicist. So as a clinician, I have to confirm that if we have an inflammation in a tissue by means of low pH and high temperature, then we're going to get the less of radiation damage in the tissue. So maybe the result, the clinical result, will not be so, good as we prefer. So this is in conjunction with what you have already showed us. But
it's not.
There is a but.
It's not.
Look,
but fine.
In fact, you showed us the very great data about the role of oxygen and FLASH. And to be honest, because I have some kind of relation with radiobiology for 20 years now. So, this is the key, the oxygen.
Yes.
We know that there must be something like a shock by the FLASH in the oxygen inside the tissue, isn't it?
So let me just answer the first one with the pH.
Yeah.
So making something acidic, you add H+. You remove OH.
Yeah.
If you remove OH, there's no damage.
Okay.
So the acidic part is you're biasing the reactions. The temperature, you do the same thing. You have to look at it as a chemical problem. If I reduce temperature, I reduce the effectiveness of the reactions. If I change the pH, I change OH levels.
Yeah.
So if you have high temperature but low pH, you have less reactions of OH. You literally wipe out OH.
There's the key point, toxicity.
So the toxicity is something else. That's a long-term effect that is affected by all the redox status of the organs, right? And the redox status of the organs is not only guaranteed by OH, it's also guaranteed by this GSH and stuff like that. But it's fun.
The GSH has its role. Okay.
Absolutely.
Has its role. But toxicity is also a key point.
Absolutely.
So, please, give us some kind of data about what exactly is happening inside. About, is really a shock in the oxygen binding coming from the flask, or
No.
it is related to something that it is really very deep inside the nucleus? What is happening? What is your feeling? We don't know exactly. What is your feeling?
So I didn't provide the explanation, so I just showed
Yeah.
that we've done it, but it's a chemical reaction. So remember that every time radiation works,
Yeah?
it works as a chemical agent. So the simplest way to remember radiation is forget the word radiation, think of chemistry. I produce a lot of reactive species, chemically, and they diffuse. So this is what I do with radiation. I produce a lot of reactive species. My natural protection of the cell, which allows you to go to the beach. I mean, I love going on the beach.
Oh, no?
This antioxidant has to be there to protect, unless I wipe them out with flash.
Yeah.
So imagine that I have a small cup like this, and this is my protection.
Okay.
This is my protection. So if I deliver radiation, I'm always protected by the radiation. But if I now deliver that amount of radiation, which is flash, you see the problem.
Yes, but I'm just wondering about what is the differentiation between the normal and the cancerous tissue?
The amount of protection. It's the key. In a healthy cell, I have this protection.
Okay.
In a cancer cell, because it's proliferating, the protection is 10 times.
Uh-huh.
So the difference is...
So you mean the enzymatic mechanics of
the redox
repairing?
No, not repair. Redox protection.
Okay.
Yeah,
okay.
the antioxidant protection is completely different because the cancer cells are accelerating their growth. They have a much higher protection because they produce more radicals. So they are used to radicals.
So
healthy cells are not.
If we have this so small time concerning the physicochemical state of what is happening inside in terms of interaction, then we're going to have the gain by this time in order to get out of the toxicity for the normal, but to gain for the cancerous. So it's we do know, but that the physicochemical is really very small. So if it is in the order of the flash therapy, you said, then we're going to have a gain
for healthy tissue.
For the cancerous cells in terms of toxicity for the cancerous cells, but not for the
cancer.
Healthy ones.
Yep.
Isn't it the case?
So it's a difference not in radiation,
Yeah.
it's a difference in antioxidant level.
Yes.
And the response comes from that.
The independent value of time now coming into this equation
Yes.
in terms, I'm telling you again, the physicochemical state. Might be the case, isn't it?
I have to understand your question better.
Because the physicochemical state is really very small in time.
Yes.
So it is in the order of the flash therapy.
Yes, but it's not the physical chemistry. It's the antioxidant timing.
Yeah.
So the antioxidants are enzymes that protect us from radiation,
We know.
right? We have different levels of radiation, antioxidant levels. So I can go to the beach.
Between
you
the
can go,
cancers and the cancers.
and the cancer and the healthy also much bigger differences.
We know that.
Exactly. And the enzyme timing is in the order of a few microseconds. But each one is different. So SOD has a half-life of around 10
So the time
microseconds.
of reaction between the cancer
Enzymes.
and
It's the enzymatic
reaction is also a key point.
Yes, the timing of the enzymes is the driver. Costas.
Great presentation and very thought-provoking. So are you saying, just to understand, sorry, I think I have a loud voice, but are you claiming that there is no role of oxygen in the flash effect to understand it correctly?
Say that again.
There is no role for oxygen?
No, there is a role for oxygen. What I'm saying is the flash, we can study oxygen effect, which is something we've not been able to do properly for years. With flash, I can try to see why this effect is occurring and then understand the oxygen mechanism. If we can understand the oxygen mechanism, we can go into then high LET, understand the rest. The flash is really a window into oxygen.
Right.
Okay, we want to treat patients, I agree,
Right.
but it's a window.
No,
it's a basic mechanism.
I'm
effect.
trying to understand the, if you're saying the radiobiological hypoxia does not happen through flash, there's some other mechanism, right?
No, biological hypoxia. Oh, you mean like in the form of, no. Exactly. There is no biological hypoxia, yes.
Chemical consumption or destruction of oxygen.
So there is no hypoxia through flash.
Okay.
What flash saturates or blocks the pathway. Think of it as a pathway, oxygen damage pathway, where you have 4 steps, and flash blocks one of them.
So my question is, which I always bring this up when we're very fascinated by this too. You do not see the flash effect in vitro, in cell lines.
We do.
We do not. We've tried, and it's not just me.
Yeah.
There's very few, if any, publications, and I apologize if you have
No, it's a very good point. It's a very good point.
With protons, with electrons, and you know, of course, Peterson's work, that he sees this only if he brings the oxygen level down.
See.
You see the flash effect in cell lines cultured in
vitro.
In normoxia?
Yes, at 21% in fact, but with the compound, not without the compound. The key point here is you need a very high dose rate. I bet you were doing 100 gray per second. Did you go to 1 million gray per second?
No, but I don't need to, because in vivo I see the flash protection.
Because in vivo you're doing healthy tissue. In vitro it's not equivalent to healthy tissue. The problem is that the redox status, if you measure it, it's completely different. The redox.
But normal tissue is normal tissue. I mean, and the people that do now the trials in patients, right? They don't see this, they don't see the toxicity. So we can have this discussion later, but it's an interesting dichotomy, and I would like to know the in vitro.
Find out after a decade, I suppose.
Yes, probably. There's a question at the back, or maybe it's finished. I didn't understand.
I have a completely different question related to flash therapy. So my question is, we are talking about reoxygenation, right? Coming from the fractionation of radiotherapy, and after a few hours, we see the effect of reoxygenation. What if you induce or you force reoxygenation through other sources, not only radiotherapy, but let's say heat?
So the problem with heat is chemically, when you increase temperature of tissue, you accelerate the chemical reactions. So what you do is the opposite. When you accelerate chemical reactions, you accelerate the benefit of radiation. So heat is good with radiation just before, while the heat is up. Alone itself is asymmetric. It depends on the spatial distribution. So there are many studies coming out of groups from Karolinska and Aarhus that show that heat is primarily advantageous with radiation just before.
Right. Yeah, I'm talking about the combined effect of radiotherapy and hyperthermia.
So he's talking about the combination of hyperthermia and radiotherapy.
Yeah. So heat would change the chemical reactions to make them faster. It will protect, so it will make it harder for healthy tissue to be flashed. Because as I accelerate the reactions, I accelerate the redox. I increase redox. If I increase redox, it's harder to flash.
So you would prefer flash hyperthermia?
Well, this is also under studies in Aarhus University Hospital, if you're aware.
They are trying to do it. It's not working so well.
Thank you.
The two methods are combined together. If we're talking about conventional radiation and hyperthermia. Okay? And of course about the comment that I have introduced in the beginning about Dr. Terzudi. So if you would like to comment on the comments, that if there is something like a relation between your method and the way that somehow might be also due to a risk model, something like an overdose to a patient in a clinical practice. And how can we use your methods in order to be sure that we have to take precautions or to take some kind of medications for this patient after this overdose problem. Please. Do you think that it will be also the case the next years to see cases like that?
So you mean to do biological dosimetry
Yes.
in the irradiated tissue?
Yeah.
This is the first way, and we have to find more advanced technologies, as I presented before, and as well more sensitive methodologies.
So what is your sensitivity?
It is much higher than the, let's say, gold standard of biological dosimetry. That is the centric analysis. The centric analysis, with the centric analysis, we can go
2 grade.
to
The prescription was
0.2 grades.
and the patient received 3 grade. Do you think it would be possible for you to
Yes, of
see
course.
this difference?
Of course, of
Thank you.
course.
Professor Theodore.
Και εγώ μιλάω δυνατά. I would like to thank all speakers. Really, it is great. Και να, sorry, I'm going to address now in Greek. Εγώ έχω να πω ακούγοντας αυτές τις 3 ομιλίες και πιστεύοντας βαθιά ότι η εξατομικευμένη ακτινοθεραπεία αφορά τους biomarkers από εδώ και πέρα, δηλαδή δεν μπορούμε να κάνουμε, ναι, δεν νομίζω ότι το είπε και ο Αλέξανδρος, το είπε και η Γεωργία, με άλλες μεθόδους, αλλά η εξατομικευμένη ακτινοθεραπεία είναι για μας το μέλλον και θέλω να τονίσω μετά από αυτές τις 3 ομιλίες στους νέους συναδέλφους ακτινοφυσικούς ότι η νέα γλώσσα η οποία θα πρέπει να μιλάμε από εδώ και πέρα είναι και η βιολογία. Πρέπει να είναι και η βιολογία. Δεν είναι μόνο, είχαμε τη φυσική, έχουμε μάθαμε ανατομία, βιοχημία, λίγο ογκολογία, ό,τι μπορούμε για να συνεννοηθούμε με τους συναδέλφους ακτινοθεραπευτές ογκολόγους.
Μην κουράζεστε. Στην UEMS, στη δικιά μας ειδικότητα, πέραν των άλλων, εισέβαλε φέτος και το θέμα του ραδιοβιολογικού εργαστηρίου.
Και εσάς και πρέπει για μας και οι μεγαλύτεροι θα δυσκολευτούμε λίγο περισσότερο, οι νέοι όμως πρέπει να μάθουν και αυτή τη γλώσσα. Είναι το μέλλον και της δικιάς μας ειδικότητας. Ευχαριστώ.
We would like to thank you all, especially Professor Seco. It was really very nice, and thank you so much for your attention. Thank you.
Coffee time.